Hello, everybody. We're going to start off with our first video lecture here. We're going to be talking about matrices, which is really the fundamental kind of building block for linear algebra. Um, and one thing that will be maybe a little annoying is that we will see matrices over and over and over, but it's going to be a little bit of time until we can really see kind of how important they are, kind of what meaning they have. We just kind of have to get into the thick of it in the beginning before we can kind of understand them. We will start off with one example that does give a little bit of kind of a college algebra um, explanation of what matrices are. But in terms of thinking about how they relate to differential equations, we got a while for that. So um, let's go ahead and jump right in. We're gonna, like I said, we're gonna start with this warm up, and then we're going to kind of talk about types of matrices, some properties they have, do a bunch of examples, give some definitions. So let's get started. So we will start with a fairly simple warm up. Um, we have a system of two equations with two unknowns here. This is a standard problem you could imagine getting in a course like college algebra. And here the goal is to just solve for x and solve for y. Um, with these equations that we have, I'll tell you that we do get unique values for x and y. So that's nice to know ahead of time. And there are a lot of different ways that you could approach this. You could approach this with substitution or elimination. If you've seen matrices, of course, you'll know that you can do this with matrices, but that's kind of what the point of this warm up is. So I don't want to do this with substitution, so I am not going to bother taking one of these equations, solving it for, say, x, and then plugging that in right here. I'm not going to bother doing that. What I'm going to do is I'm going to take this first equation and I'm going to multiply it by 2. And that's going to give me 4x plus 6y equals 8. And then if we look at this next equation, we'll see a nice thing happen where I can add these equations together and the x's cancel. Boom. Add those together, we get 12y equals 15. We get y in that case is equal to 5/4, simplifying. So we've got y. That's wonderful. Now, what you're probably going to want to do at this stage is you're going to want to take this y and you're going to want to plug it back into either of these equations in for y. I'm not going to do that. What I'm going to do is I am going to copy this again. Let's paste that. And I'm going to do pretty much the same step of work. I am going to end up subtracting the two equations from one another. So, and I will start with that times 2 there. So let's write that out. So we have that 4x plus 6y equals 8. And then likewise, we've got the negative 4x plus 6y equals 7. And now, subtracting, we notice a different thing. Put that in parentheses there. Let's give myself a little bit of extra space here. When I subtract these, the y terms cancel, and we end up with 8x equals 1. And we've got kind of a tight squeeze here, but x is equal to 1/8. And there we go, we found x. Now, this is a fairly pointed example. I created these equations to serve this kind of clean purpose here, but we have x and y. You might say to yourself, well, there was no reason to just work at the bottom. That's a lot of extra work. I could have just taken this y and plugged it in. That's correct, but there's a reason why I'm showing you all this. So when I look at this, I ask myself the following question. I say, could I notate this quicker? Could I have some quicker, some shorter notation? Let's be honest. Ink is expensive, right? So all of this writing that we're doing, it takes a lot of time, a lot of effort. Ink costs money, right? We gotta make sure we're not using too much pencil lead. So I notice in here that there are a lot of pieces to this that are kind of just fluff. And you're gonna have to bear with me here, but I think I think looking here, we have an X, a plus, a Y, an equals sign. Oh, sorry. Let me get that a little better. There we go. So we have all of these things in here. And you'll notice I'm actually just highlighting everything except the numbers. But I'll kind of point out that all of these things I've highlighted kind of just carry on throughout the problem, and they don't really do much. They don't really have much of a purpose. Like I could change these. I could put a smiley face and a frowny face instead of X and Y, and it doesn't change anything. It's really the numbers that are more important. So what we start to ask ourselves is, if I just want to do this again, with my joke of less ink, let's say, then can't I write this with just the numbers? So what if I just wrote 2, 3, 4, -4, 6, 7? And that's cool. We don't have the X's and Y's, and you could envision doing the same types of things. I could take that top string of numbers, let's call it a row, maybe that top row of numbers, and I could double it to have 4, 6, and 8. And now we're kind of at the same steps that we had before. And now you could look at these two rows and you could add them together, or you could subtract them. Wonderful, right? Um, well, this is where our first matrix comes in. What I'm going to do is, these numbers kind of just seem like they're floating in space here. Let's kind of just corral them a little bit, and let's put these little brackets on the side. Now, sometimes with this, you will see parentheses instead. So you'll see some curved parentheses there. I don't like to do that. I think that can be a little bit confusing and misleading, as we'll see as we go through the course. But so I like brackets, but you're welcome to use parentheses if you really want to. And then the last thing I'm going to do here, and you can see I kind of left some extra space in here purposefully. These equal signs turn out to be, as you would expect, important. And so I'm actually going to, instead of putting equal signs here, that maybe looks a little weird, I'm going to put a bar. And that's really just like a separator from like the left side and the right side, right? Um, and this is one of the biggest things that we are going to do throughout the linear algebra in this course, is we are going to look at equations like this, and we're going to write them in this sort of abbreviated notation, where you're going to have to look at something like this and be able to sort of envision some X's, some pluses, some Y's, and some equal signs all right in there, right? But with a shorter notation, you could now ask yourself, okay, well, what does this turn into right here? If I go here, let's take row one. I'll write it this way. Let's just say double row one. Now, this is pretty much what we did before. We times, in both these scenarios, we timed that first equation by 2. Now I'm not saying equation anymore, I'm saying row. Well, let's go ahead and double that, and let's see what we end up with. We've got that. That's awesome. Now, the same thing. We could take the 2 rows that we have here, we could add them together. Let's go ahead and notate that. I'm going to kind of work right to left here. Add rows together. And I'll verbally say this, I won't write it, but we're going to add these rows together, and whatever that result is, we're going to place that in the bottom row. That's just my choice. That's just what I want to do. So we do this. We get 4, 6, 8. Now, notice I haven't changed that top row, but let's go ahead and add these rows together, and then we put that into the bottom row, and of course we get, just like we saw before, 0, 12, 15. And I could keep going here, right? Let's go ahead and copy and paste this onto a new slide for some space. We could take this and we could say, hey, you know what? Divide row 2 by 12, right? And then what we end up with is 4, 6, 8, not changing the top row. And I get 0. 12 divided by 12 is, of course, 1. And 15 divided by 12, like we saw prior, is 5/4. Now, at this stage, I could keep going and I could try to fix this top row, but for the purposes of this warm-up example, I'm not going to bother us with that. What I do want you to see, though, is like we took this system of equations and we wrote it in just this abbreviated notation. Remember, I actually did this. I said, hey, envision, try to pretend like there's some y's, x's, equals, and pluses right there. Well, I can do the same thing at any of these matrices that I have. And if we do that here, and I'll go ahead and put this in the red, you can see that that bottom row reads exactly as y equals 5/4, right? And right there, that tells us what y is. We saw that before with our algebra back here, but we're seeing it now in this basically different notation where we're writing this stuff out in a what's called a matrix, and we're just doing these things through the rows, and it gives us the same answer, right? Um, what I will note is if you were to keep going, maybe we put a dot 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 there. This will eventually turn into the following. And just like we were talking about, you should be able to, I mean, well, maybe not right now, but this is the goal that I will have for you is to be able to take this orange matrix right here and envision it like this with these x's, y's, equal signs, and so on and so forth. And right here, I mean, I think this is pretty clear. We have x equals 1/8, y equals 5/4. This is awesome. That's great. So very simple problem, but we're just showing a different notation for doing it, right? One thing I will note here, let's actually get rid of these x's and y's in the red here so I don't clutter this up too much. Get rid of those equal signs. Zoom in and erase that. One thing I will note here, this will be important, we will see this frequently. Right here, this is a very nice matrix. This is called the identity matrix. I'll put that in green right here. Let's just say identity. This is called the identity matrix, and it serves as the sort of number one of the world of matrices. Just like maybe you take the number 17 and you multiply it by 1, you get back 17. This right here, this pattern, this kind of format that we're seeing serves that same type of purpose. So we'll keep an eye on that. We'll see that a lot during this course. So what we're seeing here, this is kind of our first example of what can we do with a matrix. And I mean, obviously we can solve a system of equations. We can kind of go back to college algebra, and this really is the first way that you're going to analyze what a matrix is, understand what you can do with it. You're basically just going to treat a matrix like this as a system of equations. And this leads me to just a wonderful example right here. Let's just write out a matrix like this. Let's go 3, 5, 0, 2, 1, 4. Let's be fun. I, E, and -1. And then let's put that same bar and let's go 10, -7, and 3, right? What you can do is you can look at this matrix and you can interpret it in a lot of ways. But for now, you can interpret this as a system of equations that looks exactly like this. It would look like 3x plus 5y plus 0z, but so I won't write that, equals 10. 2x plus 1y plus 4z equals -7. And then the fun one, pi x plus ey minus 1z is equal to 3, right? And again, right here, we have a system of three equations, three unknowns. This is totally solvable by a college algebra student. They might get scared at the pi and the e, but this is solvable. We could totally solve this for x, y, and z. And this matrix just shows us, not shows us, it just denotes, it denotes that system of equations with a bit less handwriting, with a bit less ink, let's say. So for now, this matrix is really just, it's a way to store this info. It's a way to store, I guess, the coefficients of the system of equations, right? Um, what this leads us to is we start to ask ourselves a handful of questions. Well, what can we do with these matrices? Are there certain types of matrices that are important? Are there things that we see frequently? I've talked about the identity maybe being one of those. What properties do matrices have? And that's exactly what we're going to get into next. But what I am going to do is, for a little bit, I am going to ignore this whole right side and the bar. I'm going to give us, for the most part, square matrices, but I will note they don't actually have to be square matrices. So this would be like 3 by 3. They don't have to be that. But I am going to ignore this bar notation. And I'm basically just going to say, you know what? Let's just say you had a system of equations and you really only cared about the right, or excuse me, the left side of it. And we just don't really care about this other side. So, for example, we might write something like, let's give this a name. Let's call it A equals 2, 1, 4, 8. And there we go. Now, you could take this matrix and say, well, if I put a bar here and some other numbers, now this is a system of equations. But for now, this is just a matrix, 2 rows, 2 columns. It's got 4 numbers in it. And honestly, who knows what this talks about? Who knows what meaning this has? We're just going to start doing stuff with it for now. So, um, you know what? We have this. What what happens if we just were to say triple this? What if I asked you to find 3 times A? Well, as you might expect, we just triple everything. Plain and simple, right? 3A is just, we take every entry, we triple it. Now, what if I had another matrix? Let's call it B. Let's go -3, 0, 4, and then -8. What if I wanted us to find A plus B? Let's go ahead and put this in blue, match those colors. There we go. So what if I wanted A plus B? Well, as you might expect, we just take each entry and we add them together. 4 plus 4, 8 minus 8, that's going to be 0, of course. And squeeze this in a little bit here, but we get -1, 1, 8, 0. So what we're seeing is, with multiplying a matrix by a constant, adding 2 matrices, similarly subtracting 2 matrices, you can do this kind of as you would expect. We might say entry by entry, right? So we can just do that operation to each entry right there. Unfortunately, this is kind of where the simplicity stops. We move forward into multiplication, division. If any linear algebra teacher hears me say that word with matrices, they would cringe a little bit, but we'll get there. But let's get into kind of multiplying matrices. It turns out we have troubles doing this. It is not as simple as just taking each entry and multiplying it by the other entry. So let's take these matrices A and B. We'll go on to a new slide and we'll see what happens when I multiply these. Let's paste that. Let's write this B up here. There we go. So we have these 2 matrices. You might, as I was kind of hinting at, you might hope that the matrix A times B is just what, -6, 0, 16, -64. You can see I obtained that by just multiplying each entry by the same corresponding entry. Doesn't work that way, unfortunately. So here's what we do. For A times B, now there are two different ways that we can show this work. I'll show both of them, but I'm going to write these matrices side by side. Let's go 2, 1, 4, 8. Then we'll go -3, 0, 4, -8. And this matrix, when we do this multiplication, the resulting matrix will be a 2 by 2 matrix. It'll have 2 rows and 2 columns. So I am looking for, let's put 4 little dots right there. Now, I will get into the rules for that. You could envision this getting more complicated if I had matrices that were maybe different sizes. But for now, I have a 2 by 2 and a 2 by 2. When I multiply them, I also get a 2 by 2. So let's take a look right here. I'm going to actually color code this. Let's go red right here at this red dot entry. Well, when I look at that, that red dot is in the first row and the first column. So here's how I do this. I look at the first row of the first matrix. You know what? I'm going to change my language there. This red dot is in the top row as opposed to the bottom row. So I'm going to look at the top row of the first matrix A. But then I look at this dot and I say, hey, this is in the left column. So I look at the left column of matrix B. And what I do here is a dot product. So for those that have taken Calc 3, maybe there's some students here who have not taken Calc 3 yet, or maybe you're even currently in Calc 3. If you're unfamiliar with what a dot product is, it is not that complicated of an idea. All that it says to do here is we are going to take 2 and multiply it by -3. I'm going to actually write this out. So 2 times -3. We're going to take the 1 and the 4, and we're going to multiply them. And then I just add these together. So again, if you're familiar with dot products, we are just seeing in these two things I've circled, I'm multiplying the first entries of each of them together. I'm multiplying the second entry of each together, and then I'm just adding them. Boom. And so we'll simplify this below, where what? -6 plus 4, I get -2 right there. And now guess what? I get to do the same thing. So let's go in the green right here. This green dot over here. Boom, boom. This might get a little ugly. I'm going to erase some of this right here. That green dot of the resulting matrix is in the right, let's say top row and right column. So what I do is I take the top row and the right column of A and B. Notice the order there. And I do that dot product again. I take 2 times 0 plus 1 times -8. And with that, add that all together, do the multiplication and add it together, and we get a -8 right there. Right. And we're going to keep going. I'm going to do this a little bit quicker here. We'll still color code though for this entry in here. We're going to note that it is in the bottom row in the left column. So I'm going to circle the bottom row of A, the left column of B, and I'm going to do this dot product right here. Let's write that out. And lastly, we're just going to do this one. I'm not going to do the circles and everything. Let's go yellow. We're going to do 4 times 8. Excuse me, made a mistake there. 4 times 0 plus 8 times -8. We got to fill these in, of course. -12 and 24 is 12, and then we have -64. So we have that right there. That's awesome. This result here, let's maybe clean that up a little bit, make that look a little bit nicer. We've got a 2 by 2 matrix that is the resulting multiplication there. So we've got that. That's awesome. Let me show you, and I'll do this quickly, but I'm going to show you a different way of showing your work for this. Let's copy and paste this. And what I'm actually going to do is I'm going to take this second matrix and I'm just going to move it up a little bit. And then in a different color, let's go here. And I am just going to start drawing some fun arrows. We're going to go here and here. And I know I'm kind of covering up those numbers a little bit, but right there, you can see how to obtain that top left entry. I just kind of follow the green arrows and I do the same dot product, that same multiplication that we had. And of course, when I do that 2 times -3, and then I get -6, and I take the 1 and the 4, multiply them, I get 4, I add those together, I get the -2, the same -2 that we had before. I can keep doing this. And actually, let's do this. Let's take this and just move it. I don't know. Let's move it like that. And I'll actually note that this one, maybe we do this. Maybe we draw them going down a little further, right? These arrows meet right in that bottom right entry. Do the same dot product, and that's what goes in that bottom right entry. And we saw this before. We get -64 right there. I'm going to go ahead and erase these. This is just kind of a fun, I can go here, I can go here, and now I just follow those arrows, if you will, and I do the dot product. So this is just a nice way of showing your work. Let's go right there and right there. Try to still see the numbers. I get that -12 plus 24 is 12 right there. That 64 looks a little weird. Let's make that look nicer. But there we go. Now this is nice. I can do this on the iPad, but I could take this, I could move it over, I could move this back down, and I can say, hey, there's what it equals. And this right here is the resulting matrix that we just notate as AB, just A multiplied by B. We tend not to put dots here. We tend not to put parentheses around these. We just put the letters right next to each other for that matrix multiplication. So there's a fairly straightforward example of matrix multiplication. I'm going to give us another one, and it's going to prove a kind of unique and interesting point. Let's take some new matrices. Let's go C. And this time, I'm going to give us a matrix that is not square. So this is going to be 3 rows. Let's put some random numbers in here. And then I'm going to give us another matrix that is also of the same size, 3 rows, 2 columns. There we go. Now, as we saw before, we had 2 different 2x2s, and we got a 2x2, right? 2 rows, 2 columns. Well, here we have 3x2s. Notice I say rows first, then columns. We would expect, given the last example, that when I multiply these, I'm going to end up with a 3x2. Well, let's see what happens. Let's take C times D, and I'm actually going to use this notation, that sort of trick notation that we had prior. Give me a moment while I do some copying and pasting. Let's do some shuffling around of where all this is. So there's C and D. And then CD, we're gonna do the same kind of fun notation here. So let's make that blue. And in the green, we'll put the resulting matrix, right? And the question here, the point of this example is, how many entries do I have in here? I mean, does this resulting matrix turn into a 3 by 4? Probably not. But that's really the kind of thought that we want to have running through our heads right now. Well, let's go ahead and just try the top left entry. I maybe don't know how many things are in this matrix in full, but I know that there's going to be something in the top left. So when I do that, I'm going to take this right here. We're going to draw the arrow down. We're going to take this right here. We're going to draw the arrow down. We see those arrows meet in that top left entry. We go, sweet, let's go ahead and do that dot product. So we take the first entry, the first entries, I'll say, plural, the 1 and the -3, we multiply them. We take the second entries, the 4 and the 0, we multiply them. And then we take the third, oops, there's no third entry, right? So we're seeing an issue here where I can't do a dot product of the top row of C and the left column of D because they don't have the same number of entries. And right here, we're stuck. We're done. There is no way to multiply these two matrices. We can just go, we can just cross this out. This doesn't work. We don't like this. And this does give us a rule, actually, and I'm going to write this rule out. This rule states that when multiplying matrices, excuse me, when multiplying matrices, the columns, and you know what? I'm going to change my notation here. A and let's do this. A and B to get AB. Say it as I'm writing it. The columns of A have to match the rows of B. I will write this out in a different way as well. I'll say that if we have A, B, we have to have, let's say, M by N, and then N by R, let's say. So when we do this multiplication, you can see those N's, they have to be the same. That's the only way that this works. And you can see this with this last example. When they're different, I end up not being able to do this dot product. It fails. But if they were the same, then, which I'll show an example of that, then we're sitting pretty, right? And so when we do this, we get a resulting matrix. And the question is, what size is that matrix? Well, it's M by R, interestingly enough. And we'll see a fun example of this. I'll do something crazy like a 5 by 3 and a 3 by 7, and we'll see what happens, right? So let's go ahead and let's do exactly what I just said there. Let's take A, which I said 5 by 3. So 5 rows. I'm just going to kind of number these sequentially. 5 rows, 3 columns. I'm not going to do a 3 by 7, but let's do B equals, let's go 3 by 2. That's fun. So let's go 1, 2, 3, 4, 5, 6. And right there, I'm just kind of checking my work. So we have 5 rows by 3 columns, and here we have 3 rows by 2 columns. I can already say this is going to work, and let's write this out. When we do A times B, I'm going to do some copying and pasting. We will not work out the entirety of this because that would take a long time, but let's also use our fun notation here where we move this up just a little bit. Oh, there we go. I'll move this back down and make this look a little bit prettier in just a second. But right here, we're going to end up with a matrix in here. And let's take a look. Let's go down right there. Let's go across right there. And you can see I can do a dot product here. I can take the 1 and the 1 and multiply them. I can take the 6 and the 3 and multiply them. And I can take the 11 and the 5 and I can multiply them. And whatever that dot product turns into, that's that number right there. And then likewise, watch as I just move this down. Now the next entry, I'm going to fill this all in. This will be fun. I can just take these arrows and I can move them accordingly, and you can see that all of these dot products will match up, and they will have the same number of entries because the number of columns right there, 1, 2, 3, matches the number of rows, and this dot product is multiplying the rows of A by the columns of B, and so this works out. And of course, excuse me, didn't mean to erase that. The resulting matrix here, you can see it is a 5 by 2, right? So this is actually a 5 by 2 matrix that has 5 rows and 2 columns, right? So fun matrix multiplication examples. You can work through a plethora of those on your own, but keep in mind that in order to do this matrix multiplication, we have to follow this rule that the columns of A have to match the rows of B. So, and you know what I might do? I might change this from R. Let's change that to like, let's just put P. I don't, R looks like rows. I don't want to confuse us there, but great. There we go. So there's some multiplying matrices, some good examples, some bad examples. I have talked about dot product, and with that, I want to give us some more definitions here related to that. So we're going to see scalar product and dot product. These might be things that you've seen in Calc 3 if you've taken that, or that you're probably soon to see if you are in the middle of taking Calc 3. But let's go ahead and kind of formally define these. So with these definitions of scalar product and dot product, I have to give us one, not really a definition, but one thing to note. Let's notate the vectors that you might, an example of a vector that you might have seen in Calc 3. Depending on who was your Calc 3 instructor, where you learned Calc 3, you might have seen a handful of different notations. You might have seen this notation here. You might have seen it written as 3i hat plus 1j hat plus 2k hat. Maybe you saw it written like this. And I'll say even better, maybe you saw it written like this. All of these things that I have written, all 4 of these things are, I'm going to put air quotes, the same. These two, some mathematicians would argue that these are different. I think for our purposes, these are we'll kind of treat them the same. But what I want you to get used to here is this whole IJK hat that you may have dealt with a lot in Calc 3, and maybe had written it in this notation with the little greater than less than signs. Not that that's what they represent, but with these little symbols here and commas, these are vectors, right? But if I look here, and particularly maybe at this one, this contains the same information as up here, but this looks an awful lot like the matrix stuff that we've been seeing. And this is, in fact, a matrix, and I will note this. Um, this is a 3 by 1 matrix. So we've seen plenty of examples, and I'll scroll back here, but we've seen plenty of examples of say 2 by 2 matrices. Back here, we had 3 by 2 matrices right here. We had fun ones. We had 5 by 3 and 3 by 2 and a 5 by 2. There's nothing stopping you from having a matrix that only has one row or one column. Um, and then likewise, this right here, this would be a 1 by 3 matrix. And this is the first thing uh, with regards to vectors that I want you to sort of ingrain in your head. Vectors are a form of matrices. Um, so you could say the age-old classic, all vectors are matrices, but not all matrices are vectors. We've seen a handful of matrices here that definitely are not vectors, like we've seen maybe in Calc 3, um, or even in physics courses, say. Um, so what we're going to do pretty much for the next bunch of weeks here as we do linear algebra, you're not going to see me write this notation out much at all. I am going to stick to this notation here. Um, this notation is far more common in the math world, whereas this notation is far more common in the physics world. But we're pretty much going to stick with this matrix notation. So with this, we, as I hinted at, and let's talk about scalar product and dot product. Well, we have done dot product. Um, well, maybe you've done dot products in Calc 3 if you've taken Calc 3. But if I have, let's say, two vectors, and again, I'm going to write them using my notation. Let's go 3, -5, 0, and then let's write v is equal to 1, 6, and 4. If I do a dot product of these, we would notate that with a dot there. And I'll note, going back, I told you with matrix multiplication, where was it? I said right here, I said, we typically don't put a dot in here in between the matrices. That's because we don't want to confuse ourselves between matrix multiplication and dot products. So here we have a dot product, and if you know how to do this, wonderful. If you don't, that's totally fine. I'm now realizing I probably should have defined this before we did matrix multiplication, but here we are. So we have this, let's put the little dot in between them. By definition, we just take each entry. I'm not going to use a dot right there. Let's put some parentheses. We take each sort of corresponding entry, let's say the first entries, the middle entries, and the last entries, and I just multiply them all together and I add them up. So 3 -30 is -27, and of course last one is 0. So we get -27. This is a dot product right here. The dot product has lots of meanings. Most notably for our course, if you got 0 for this, that tells you that these two vectors are orthogonal to one another, that they're perpendicular. And again, if you recall from the Calc 3, you may or may not have taken one definition of the dot product is, I need some magnitudes here. There we go. Is that I'm not really focusing too much there, but you can envision how a certain angle would yield a dot product of 0 and how that talks about orthogonality. So that's fun. That's great. This is dot product. Let's go ahead and write that on the page. Dot product. Wait, so we have a dot product with two vectors there. The question is, what the heck is a scalar product? And I'm going to whisper this because I don't want anybody to hear me say it. A scalar product is the same thing as a dot product. It's just when instead of having two column vectors, these are vectors that are just a single column, I'm going to take one of these vectors. Notice I'm copying and pasting the page. This is bad. This is really bad. I shouldn't be doing this. Scalar product, same thing. The math gods are going to curse me. I know I erased right there, but pretend I didn't. If I just went 3, -5, 0, same numbers, um, just in a row vector, right? Instead of a column vector this time. This scalar product, interestingly enough, is also notated with a dot. This is really, really, really getting at the point that I'm trying to make, that for most intents and purposes, scalar products and dot products are the same thing. It just kind of depends on how your vectors might look, if you have 2 column vectors or 2 row vectors. Honestly, most of the time, if you have a row vector and a column vector, a lot of times people just say, oh yeah, the dot product, and they will actually show their work changing this row vector to a column vector. They will just write this page right here, even though it was a row vector, not a column vector. It's honestly, these are pretty much the same thing. Your book outlines this fairly well. You can, Google the differences between these, and they do have some meanings here, but um, for our purposes, pretty much the same thing. So we have that. That's wonderful. One thing that this brings us to, I've maybe been, I've noted that some people get a little loosey goosey with taking a vector like this and just sort of flipping it, right? Just rotating it so that instead of a row, it is a column vector. And this asks the question, or this brings up the question: what if I did this with a matrix? Um, so what if we took a matrix A? Let's call that M. I've used A already. Let's go M equals, let's go 1, 2, 3, 4, 5, 6. I could probably be more creative and use some different numbers there, but I'm actually going to do this for a reason. Um, what if we took this and we just sort of turned it on its side, right? Maybe with some air quotes. What if I turned this from a column vector, air quotes, to a row vector, air quotes? Of course, this is not a vector, it's a matrix. But interestingly enough, I can say, well, wait a minute. If I were to take this row vector and just write it as a column vector instead, isn't that just taking this row and turning it into a column? What if I took the rows of this and turned them into the columns? And what we're going to see here is, if I rewrite this, and I'm going to be a little pointed with how I write this. What I have done is I have taken this top row and I have made it the left column. I've taken the middle row and made it the middle column, and I have taken the bottom row and made it the right column. Honestly, you can kind of like turn your head 90 degrees, and that kind of does the job. Um, this has a name. It also has a notation. This is the transpose of a matrix. And I'll say this, just like matrix multiplication, just like multiplying a matrix by a scalar, just like adding two matrices, this is an operation that can be done to a matrix. So you can take a matrix M and you can say, I'm going to transpose it. We label that with M exponent T, and then boom, we have the transpose of it. And all a transpose does is it switches the rows and the columns with one another. So that's fun. There we go. Um, there's another operation of matrices. Um, to continue on here, let's talk about sort of the properties of the transpose of a matrix, because there are some fun ones here. I'll go ahead and write this out. Properties of transposes. As you might expect, if I take A transpose and I transpose that, it just takes me right back to A, right? Take a matrix, switch the rows and columns, switch them back again, you get the same thing, right? Um, if I take two matrices that are added together and I want to transpose that, it interestingly enough is the same as transposing each matrix individually and then adding those together. Very similarly, a matrix multiplied by a constant k, then transposed, is the same as k multiplied by the transpose of just the plain matrix A. Lastly, if I take two matrices that are multiplied by one another and I transpose that, fun enough, the result is B transpose A transpose. And that's cool, right? This last one is definitely a little weird. Um, there are ways to prove that. You could even just Google that if you want to see a proof of that. Um, Proofs are something that we won't emphasize too much in this course. I wish I could, but I just don't really have a whole lot of time to do that. So I definitely recommend that you look at proofs. But what we're seeing here is that addition and scalar multiplication, right? Addition, subtraction, let's put a little plus minus there. Those usually work out nicely with matrices, but multiplication does not, right? And this leads me to, what are some properties of just matrices in general? I mean, I'm maybe going all out of order here, but I have shown you now all these properties of transposes. But what about just matrices? What if I just was given a handful of matrices, A, B, C, um, and I just wanted to see, what can I do with these, right? Um, well, there are a lot of things that we can actually do with this, and I'm going to start writing these down. So let's write this a little bit more formally. So given matrices A, B, and C, we have the following. Now, I'll preface all this. I am going to be writing out some matrix multiplications here. All of this is assuming that you can even do the multiplications of these matrices, right? We saw examples where we had two matrices that you could not even multiply by one another. So of course, that's not the scenario that I'm talking about. But let's go ahead and let's start writing things out. If I have AB multiplied by C, that is the same as A multiplied by BC. If I have A multiplied by B plus C, that is the same as AB plus AC. That's the distributive property. That's fun. Likewise, B plus C times A, again, distributive property, is BA plus CA. I'm going to pause for a moment. Why have I shown you two different distributive properties? Think about that for a moment. We'll talk about that a little later. Let's keep going here, though. I am going to introduce some new notation. Let's put a little bar there, divider bar. A multiplied by I is equal to A. And you might be wondering, okay, what the heck is that I? This I is effectively kind of like a 1, right? We actually saw this before. I'll write this down in the bottom corner. But I is just the identity matrix, I for identity. It is a square matrix always. I have written down there in the bottom right, I wrote a 2 by 2, 2 rows, 2 columns, but it could be a 3 by 3. It could be a 4 by 4. And in fact, actually, I'm going to change this. Let's write out the identity. Let's go I3. This is 1, 1, 1, and I have zeros everywhere else. So just ones along the diagonal and zeros everywhere else. And you can check this with any matrix you want. If you take a matrix and multiply it by I, you will end up with that same matrix you started with. Now I'm going to do a similar thing here. I'm going to write I times A is equal to A. And you're probably looking at that and you're going, it's the same thing. Why does he keep writing this twice? As you might be thinking and guessing at, there could be a difference between these two things right here. We'll see an example of that in a moment. Lastly, this one's probably fairly obvious. If I take a matrix A and I multiply it by the zero matrix, I'll explain notation in a moment, I end up with the zero matrix. Same thing if I take the zero matrix and I multiply it by a matrix A, I get the zero matrix. Notationally speaking, usually what happens in textbooks and on the internet, when there's a matrix, we bold it. I can't bold in handwriting, so I've adopted this notation here. This is a zero with a subscript m and n. That is me just saying I have a matrix that consists entirely of zeros. It has m rows and n columns. Again, so long as this matrix multiplication even makes sense to do, if you do this, you end up with the zero matrix. Largely speaking, what I might even do is I might even just erase all of this and just sort of bold. there's a bold zero. So that's a zero matrix right there. Just a matrix that has all zeros. So I know that looks weird and funny, but there we go. Cool. So we see all these things. This is just things like commutative property, associative property, distributive property. They hold for matrices, but we are seeing an interesting thing here where I'm hinting at maybe the order in which I multiply matrices could matter. And in fact, it does. The multiplication AB is not necessarily, it can be, but it's not necessarily the same as BA. I'm not going, for the sake of time, I'm not going to give us examples here. I'm not going to write out examples, but I will go back to the matrices A and B that we defined here. And you can see the work for A times B. I implore you, take these matrices and do B multiplied by A. You will not get the same thing that we had here. And again, that doesn't always happen. You could get lucky and they happen to be the same, but in this example, it won't. They won't be the same. So something to keep in mind here with this is the order of matrix multiplication matters. I'm hinting at maybe solving equations that have matrices in them. That's a mouthful. We'll see what that means, but we'll get there. Mostly look at maybe these two examples right here and go, why did he bother writing out two different examples here? One where it's A multiplied by B plus C and one where it's B plus C multiplied by A. Well, they in theory could be different. So I need to make sure that I show the distributive property for each of them. Interestingly enough, we're seeing an example here where A times I is in fact the same thing as I times A. That's fun. There's a good example. And we're also seeing it here. A times the zero matrix is the same thing as zero times the A matrix. But that doesn't always happen. So got to be careful there. Wonderful. Kind of taking a deep breath here, and then let's go into kind of a shift into some different things. Let's look at some particular types of matrices. We've hinted at a handful of them already. We've talked about how vectors are matrices. And you know what? I'm going to go ahead and write that. Let's put that as the first bullet point. Vectors are a type of matrix. That's awesome. What we've also seen, though, is we've seen the identity matrix. That's that matrix with ones along the diagonal and zeros everywhere else. In the same breath, we saw the zero matrix. Not a very fun matrix, but it's there. We could also have two other types of matrices: diagonal matrices and triangular matrices. And I'll write out some examples of these. But a diagonal matrix is just a matrix. I'm going to note it with D for diagonal. It's a matrix that has some numbers along the diagonal, however big that diagonal is. But everything else is just zero. I'll put some big zeros there, right? So all of the other entries are zero. Similarly, I could have triangular matrices. I'm going to do R and L. And a triangular matrix, if I say it is a, and you know what? Sorry, I'm going to change that to U and L. You'll notice I'm just kind of using whatever letters I feel like using here. It doesn't really matter. But U would be a upper triangular matrix. So this would be an example where I have some numbers along a diagonal. I also have some numbers up here. And then I have zeros all down in the bottom right there. A lower triangular matrix, same thing, just flipped. Whole bunch of numbers on the lower portion of this matrix, but then just zeros all up there. If in addition to a triangular matrix, your diagonal is also all zeros, then we would say it is a strictly upper or lower triangular matrix. So that's cool. Wonderful. Some fun types of matrices. One thing that I do feel like I need to mention when we're talking about vectors here is the definition of linear combination. I'm going to do this on a different slide. This is a word you're going to hear me say a lot during this course. So let's go ahead and write this out: linear combination. This applies to vectors, it applies to matrices, it applies to functions, it applies to numbers, it applies to pretty much anything mathematical that you can think about. A linear combination, and I'll define this with vectors, but remember, this can be, I could do this with functions, I could do this with matrices, I could do this with a whole bunch of things. A linear combination of vectors, U and V, is defined as du plus dv, where c and d are just real numbers. They're just constants, right? Basically, if you take two vectors, two functions, two matrices, to anything, and you do two things: you multiply each of them by a constant, so you scale them, and then you add them or subtract them. That the combination of those two things is by definition a linear combination. So if you ever, if we're in class and you see me, I'm holding two functions and I say, let's take a linear combination of these. That is, multiply each of those constants by a scalar and then add them together, right? A useful definition, we're going to see that frequently. So whole bunch of stuff. I do apologize if this lecture is seeming kind of all over the place. This is really just the start of matrices. There's just a whole bunch of stuff that we have, and we kind of just throw it all out there and call it a day. We are going to wrap up a little bit here and ask ourselves, what else are we missing with matrices? And I'll go ahead and answer that question. It's division. We've seen doing scalar multiplication of a matrix. We've seen adding matrices together. You 100% have added vectors before in your life. You've scaled vectors. You've done a dot product, which is multiplying vectors. We've done examples today of multiplying matrices. But where the heck is division? And it turns out that division does not exist for matrices or vectors for that matter. But this leads to an interesting question of, well, what if we had like an equation? What if we had a problem that had matrices in it that we wanted to solve? I'll give us an analogy. Very, very, very simple analogy. 2x equals 6 for an algebra student, they would divide both sides by 2, and they would say x is equal to 3. Done. Simple. But what if for us, what if we have a matrix A multiplied by a vector x, and this results in a vector? If it helps, for example, what if A was like 3 by, what if it was a 3 by 3? And I'll just write A 3 3. So 3 rows, 3 columns. And then X is 3 by 1. So it's a vector that is 3 by 1. And then B is also 3 by 1. It has to be actually by our rules of matrix multiplication. Well, we can actually write out what this might look like. This would be something like this. Just put a whole bunch of little dots here. This is, albeit a bit more complicated, this is pretty much the same thing as the simple algebra 2x equals 6 solve for x. And you might say, hey, to solve ax equals b, let's go ahead and go to a new slide while we're here, but to solve this, I could just divide both sides by a. And I have x equals b divided by a. Unfortunately, doesn't work. Not at all. So we have to find something else to do. Well, going back here, if this were an in-person lecture, I would pause for a moment and I would say, hey, how would you solve this without division? Take a moment to think about that. If you want to, pause the video now and take a moment to think, how would you solve this without using division? Now, the answer to this is to just do multiplication, but you would do multiplication with an inverse. So I know I'm kind of scribbling here a little bit, but let's just write this out. 2x equals 6. I'm not allowed to use division. Okay, that's fine. I'll multiply by 1/2. That will solve our problem here. Now, I will also note, though, I'm going to use some different notation. I'm going to multiply by 2 inverse. You wouldn't usually put that there, but that's fine. That would work. And now I note that 2 inverse multiplied by 2 is just equal to 1. So I have x equals, and again, you've never probably thought of numbers this way, but 6 multiplied by 2 inverse, it is in fact 3. So what if I did the same thing with these matrix stuff? If I have ax equals b, well, what if I multiplied both sides by a inverse? But I want to be very clear. Watch what I do here. I'm going to move this b over a little bit. I am going to multiply by a inverse on the left side of each. Let me rephrase. Of this equation, I have a left and a right side, but I am going to multiply each of these circle things by a inverse on the left, right? As we saw, doing matrix multiplication matters. If I do b times this a inverse that I'm writing and a inverse times b, those could in theory be different things. So this is important. We have to make sure that we do that. There are so many questions that are happening here. First and foremost, what the heck is this A inverse, A negative one? What even is it? How do I find it? Why is it useful? And you know what? I'm not going to tell you all of that right now. That'll be for a future lecture. But I will show you that this does, in fact, give us an answer to this problem, right? We are going to spend a good chunk of time uh, seeing this, exploring it, doing tons of examples. So don't feel, if you feel lost, if you feel like you're yearning for more here, that's okay. But so we will see a bunch of it. Um, but one last thing that I do want to mention, I've been writing this AX equals B all over the place. I'm going to write it one more time here. And I am going to note this is something, again, that we are going to see lots of. But I want to tie this back to something that we have seen already. I want us to notice, you know what? Let's just do some fun example. Let's make a matrix A, 3, 2. Um, you know what? Give me a moment here. Let's go 3, 5, 0. We're going to go, I promise I have a reason for this. We're going to go 2, 1, 4. We're going to go pi e negative 1. Now, this x vector here, through what we were kind of hinting at before, in this algebraic equation, x is the thing you don't know. Well, similarly here, x is the thing I don't know. And since I don't know it, let's put some variables there. Oh, I don't know, x, y, and z equals. And this b vector, let's pause for a moment. Let's ask ourselves, what does this b vector have to look like? Well, this a is a 3 by 3, and this x is a 3 by 1. As we saw before, sort of cross out the middles, this has to be a 3 by 1 in result. When I do this matrix multiplication, it is a 3 by 1. And so I'm going to write out a 3 by 1, and I'm just going to make up some numbers here. I don't know what these could be, but maybe for example they're 10, negative 7, and 3. And this is great. What we have done here is I've really just given you an example of what an a times x equals b might look like. I have some matrix, this 3, 5, 0, 2, 1, 4 pi e negative 1, multiplied by some unknown vector, and that equals a vector that I do know, 10, negative 7, 3. And looking at this, we ask ourselves, how the heck do I solve this? We saw two things. I'm not allowed to divide by this matrix. That's on each side, not allowed, because we don't have division of matrices. I could maybe do this A inverse tactic to give me an answer for X. But at the current stage in time, I don't know what A inverse even is. I don't know how to find it. I can't look at this matrix and just say, oh, A inverse is this. I don't know how to do that. So what else can we do? Well, let's actually work out this matrix multiplication right here. If I do this, I take this row times this column, and you'll notice something fun happens. That's 3x plus 5y plus 0z. And I will refresh ours. This has to be, I'll write this down here. It has to be a 3 by 1. It has to look like that, just one single entry. That top one, as I had just verbally said, is 3x plus 5y plus 0z. I won't bother writing. Well, now I do the middle row times this column, 2x plus 1y plus 4z. And I do the last one, pi x plus EY minus 1Z. And of course, this is still equal to 10, negative 7, 3. This is a 3 by 1. This looks weird. This looks big. It looks like a matrix. This is a vector with one entry, one entry, one entry. And it is set equal to a vector that has a top entry, a middle entry, a bottom entry. So guess what? All of these have to be equal to one another. And this is going to be a great fallback. I know that 3x plus 5y has to equal 10. The top entries of each of these vectors have to match. I know that 2x plus y plus 4z has to equal negative 7. And I know that ix plus ey minus z has to equal 3. Where have we seen these before? If we go all the way back to almost the very beginning, I had written this up as an example of taking a system of equations, three unknowns, and writing it in this format instead. I'm going to copy and paste this right here. And I'm going to bring this to our most recent slide. Make that a little tinier. I'm going to color that as well. Put that in green. This is sort of a wrap up of this lecture, as well as looking ahead at what we're going to see. If you have a system of equations, you can write that system of equations like this. And then by doing sort of a backwards, undoing matrix multiplication, you can take this right here and you could write it as a multiplication of a matrix times a vector that you don't know what that vector is. We don't know what x, y, and z are. But now I have this. And if you want to, you can totally write this in the succinct format, ax equals b, where you have some names, right? This is a, this is x vector, this is b vector. That's wonderful. But what you could do instead, not instead, but what you could do is you could take this right here and you could say, you know what? I'm going to get rid of all the fluff. I'm going to get rid of this x, the y, the z's, the equals. I'm going to get rid of all of that fluff. And I'm going to replace it with a vertical bar. And this brings us right back to this notation that we had used in the very beginning of this in the warm-up. Let's go back there. Back in this warm-up, we looked at how I could solve a system of equations, almost pretending like I was a college algebra student. Now we saw, hey, I can get rid of the fluff and I can write it in this notation, in this matrix notation that has a bar right here. And I can do the same actions as I would have done in algebra class. I can do the same actions and it ends up giving me my answer right here. Well, we saw, we saw this as well. I didn't solve this, I didn't finish this, but we saw, hey, here's a system of equations. Let's write this in a matrix with a bar. Well, we're seeing the same thing down here, where this matrix with the bar could instead be written, I guess let's call it longhand. It could be written like this, and this right here is ax equals b. And what we've seen sort of that we can do is we can solve this with what is called a inverse. And that is our next lecture. We are going to look at a problem like this. For fun, I might even take this same exact problem, maybe without a pi and an e, maybe I change those, and we'll actually solve that. We'll do this in a multitude of different ways. We'll do it with an inverse of the matrix. We'll do it manually by just sort of algebra style, and we'll see how this all sort of ties together. But I'm hopefully giving you a little bit of some connections here. By and large, matrices are important. They store info. They help us solve systems of equations in, I guess, an abbreviated way, save some ink. We like that. we're gonna keep exploring these a lot and see kind of some properties of these things. But for now, we're gonna go ahead and end that. I hope this wasn't too long of a lecture. Um, but with this, we will move on and we'll have some more Zoom lectures that are, quote unquote in person. But for now, this will be it. So thanks for tuning in. If you have any questions, don't hesitate to email me. And there we go.